Hello, my name is Rico-Sotelo, and the topic I will be covering is Chapter 18, Aqueous Ionic Equilibrium, and we will be determining if mixing each pair of solution results in a buffer. The problem reads, determine whether or not mixing each pair of solution results in a buffer. We are given A, 15 milliliters of 0.10 molar of hydrofluoric acid and 135 milliliters of 0.175 molar hydrochloric acid. B, 150 milliliters of 0.10 molar hydrofluoric acid and 55 milliliters of 0.15 molar sodium fluoride. And C, 125 milliliters of 0.15 molar methylamine and 120 milliliters of 0.25 molar methylammonium chloride. Essentially, we are trying to determine whether mixing these solutions creates a buffer or not. So what information do we have? To begin, we know the volume of each component. We know we have 15 milliliters of HF and 135 milliliters of HCl for the first problem. We have 150 milliliters of HF and 55 milliliters of NaF for the second problem. And finally, we have 125 milliliters of CH3NH2 and 120 milliliters of CH3NH3Cl. We also know the molarity of each component. We have 0.10 molar HF and 0.175 molar of HCl for part A, 0.10 molar HCl and 0.15 molar NaF for part B, and 0.15 molar of CH3NH2 and 0.25 molar CH3NH3Cl for part C. We also know what solution pairs we are mixing together to try and create a buffer, these pairs being HF with HCl, HF with NaF, and CH3NH2 with CH3NH3Cl. We will go over a few definitions in order to see what makes a successful buffer. To start off, a buffer is a chemical solution that resists pH change upon the addition of an acid or a base. We should know that a buffer contains significant amounts of a weak acid in its conjugate base or significant amounts of a weak base in its conjugate acid. This allows the acid to neutralize any added base, or vice versa, in order to minimize the change in pH. It is important that our buffer is made up of both a weak acid in its conjugate base or a weak base in its conjugate acid, seeing as how a weak acid or weak base by themselves do not hold sufficient amounts of their conjugates to resist a change in pH. If we want to make a successful buffer, we cannot surpass the buffer capacity or buffer range. We define the capacity of a buffer as the amount of added acid or base which our buffer can effectively neutralize, while the range of a buffer is defined as the pH range over which a particular acid and its conjugate base can be effective. The most effective buffer range is when pH equals pK plus or minus 1. Surpassing the capacity or range of a buffer essentially defeats its purpose. Finally, the base to acid ratio for an effective buffer must be in between 0.1 to 10. To start with problem A, we have to first identify the two solutions being mixed. In this case, we are mixing HF, a weak acid, and HCl, a strong acid. As per our definition of a buffer, we know that we have to mix either a weak acid with its conjugate base or a weak base with its conjugate acid. In this problem, however, we have only a weak acid and a strong acid. This cannot make a buffer, seeing as how the weak acid does not have a conjugate base to counteract any added acid, and the strong acid by itself can also not make a buffer, as it ionizes completely. Therefore, this mixture cannot make a buffer. For problem B, we identify the two solutions being mixed, and we see that the solutions are HF and NaF, a weak acid and the basic salt that contains its conjugate base. To prove this, we simply show the dissociation of each. After we dissociate, we see that the NaF salt contains a conjugate base for the hydrofluoric acid, and that the dissociation of the hydrofluoric acid also produces its conjugate base. We then observe the buffer system and notice that the hydrofluoric acid neutralizes any added base into water and the F- ion, and that the F- ion is neutralized into hydrofluoric acid when we add a proton. To ensure that this is an effective buffer, we then find the ratio of base to acid. As long as it is in the range from 0.1 to 10, then we know it is effective. We calculate the ratio and find it to be 1.5, indicating an effective buffer. We utilize the Henderson-Hasselbalch equation to determine the buffer range. Remember, we do not necessarily have to find the pH, but rather just see if the log of base over acid is equal to plus or minus 1. We implement our concentrations into the indicated equation and find that the log of the concentration comes out to 0.176, which is still within range. Since no strong acid or strong base were added, we need not determine the buffer capacity. Therefore, mixing these two solutions does result in a buffer. For problem C, we once again start out by determining the solutions we are mixing, these being methylamine and methylammonium chloride. Methylamine is a weak base and methylammonium chloride is an acidic salt. We can now dissociate both and notice that methylamine produces its conjugate acid when dissolved in water, and the methylammonium chloride produces methylamine when dissolved in water. We observe this buffer system and we can see that the methylamine neutralizes any added acid, since it's the base, while the methylammonium ion neutralizes any added base, as it is the conjugate acid. We find the ratio of base to acid and find it to be 0.6, determining it as an effective buffer. We use the Henderson-Hasselbalch equation once more to find the buffer's range. After implementing our concentrations, we can see that the pKa is only subtracted by a value of 0.222, keeping the buffer well within range. Again, since no strong base or strong acids were added, there is no need to determine the buffer capacity. Methylamine and methylammonium chloride do indeed mix to become a buffer.